Next up we have the present value of an annuity, where we're going to take sort of the opposite viewpoint here. Essentially we're asking, if I want to establish an account that pays me or from which I withdraw a fixed amount periodically, how much money do I need to deposit in the first place? How much money do I need to deposit in this account to make this happen? Or to be very precise, here's a particular example behind me. So suppose we want to establish an account from which we would withdraw $1,000 every 6 months for the next 3 years. And at the end of the 3-year period, the account is empty. The account balance is 0. The question is, if the account pays 6% compounded semi-annually, how much should we deposit in the account? So what are we withdrawing total? We're withdrawing a total of 6 months for 3 years, $1,000. That's $6,000 total, right? 6 withdrawals of $1,000. We would expect that we shouldn't have to deposit $6,000 to withdraw $6,000, right? Because the money we originally initially deposit is going to be compounded. So we would expect to have to deposit something less than $6,000, but again, it's a complicated problem, right? Because after you make your first withdrawal, there's less money in the account, so less money that's earning interest. After you make your second withdrawal, there's even less money in the account, so even less money is earning interest. So what's happening here is, again, it's one of these geometric series problems, and we're going to proceed exactly as we did in the last section, where I'm going to draw a timeline and sort of establish exactly what's going on at every single time frame. So I'll be right back with you here. So once again, here's our timeline, right? 3 years total, starting off at now. Here's 0 years, then 1, 2, 3. And our number of periods, because we're making these withdrawals semi-annually, we've got 6 total periods, right? 2 per year. So let's think about this. At the end of the first period, we withdraw $1,000. The question is, how much should I deposit in the first place to have this $1,000? Well, again, it's a compound interest problem, right? And we've got our compound interest formula for the amount. A is P times 1 plus I to the n. So I know my amount. I know my future value. My future amount is $1,000. What I want to solve for is the present value. How much should I deposit to have this $1,000 at the end of the day? So we're solving for P here. Divide both sides by 1 plus I to the n, or I can write that as a negative exponent. That's A times 1 plus I to the minus n. So what's my present value of this $1,000? How much should I deposit? Well, I deposited 1,000 times 1 plus I to the n. So what is I? Our annual rate here was 6%. So per period, semi-annually, 6% divided by 2 is 3%. So this would be 1.03. And we're looking at 1 period to the minus 1. What about the second $1,000? What's the present value of that money? How much should I deposit to have this second $1,000? Well, I deposited 1,000 times 1.03 to the minus 2. A little bit less, right? A little bit less because this money has been compounded twice, as opposed to this first $1,000 was only compounded once. And then you go down here to the third $1,000. You can see the pattern here, right? This is going to be 1,000 times 1.03 to the minus 3. Present value of the fourth, 1,000 times 1.03 to the minus 4. 1,000 times 1.03 to the minus 5. And last but not least, the final $6,000 or the final $1,000. This guy's been compounded 6 times, so the present value is 1,000 times 1.03 to the minus 6. So all of this is the present value of these future amounts of $1,000. So how much did I have to deposit? Well, I had to deposit the sum of all of these values. And so the present value of all payments is the sum of all of these things. 1,000 times 1.03 to the minus 1 plus 1,000 times 1.03 to the minus 2 and so on, add them all up. Plus dot 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 plus 1,000 times 1.03 to the minus 6. So again, you plug this into a calculator, you compute this, but once again, this is tedious. If I have many more payment periods, if you have hundreds of them, it's very, very tedious. But once again, this is what's called a finite geometric series. There's a nice mathematical formula for adding up finite geometric series, finding the value of these things. So once again, if you want to see that, it's in the textbook, but I'm just going to give you the final formula. So here it is. Here's the present value formula for an ordinary annuity. It looks quite a bit like the future value formula, but it is different. And it says that PV, so PV for present value is equal to PMT. PMT is the same as before. It's the payment, the payment size, so the amount you're going to withdraw every period, times 1 minus 1 plus I to the minus n over I, where I is the same as before. It's the rate per period, so it's R over M, and N is the total number of periods, so M times T. So here's the formula, and once again, you'll have questions where, for example, we're going to use this right now to find the present value of an annuity, but you'll have other questions where 3 of the 4 values here are given, and you have to find the 4th. So let's do an example. So our first example is just a straight up present value question. It's how much should you deposit into an account paying 8% compounded quarterly in order to receive quarterly payments of $1,000 for the next 4 years. First thing I want to observe is how many payments are we getting? Quarterly payments for the next 4 years, so that's 16 total payments of $1,000, so we're going to withdraw $16,000. So what am I expecting? Am I expecting to definitely deposit something less than $16,000, right? Because the amount that we originally deposited is going to compound and increase in value, so it should be something less than $16,000. But all we have to do here is go straight to our formula. So PV is PMT times 1 minus 1 plus I to the minus n over I. And now we just have to plug in all these values, right? We want to find the present value. So present value is going to be payment size, 1,000 we said, times 1 minus 1 plus I. What is I? Well, our annual rate is 8%, and we have 4 periods per year. It's quarterly, so it's going to be 0.08 over 4 to the minus n. What do we say n was? It's the total number of periods. So we have 4 periods per 4 years. 4 times 4 is 16 total periods. Over I once again, over 0.08 divided by 4. And that's it. Plug all this into a calculator. Be careful with your rounding as always. But I get, remember we wanted something slightly less than 16,000. This is 13,577.71. So we would make this initial deposit, and then we'd be guaranteed over the next 4 years to be able to withdraw 16,000 total. Sort of a good deal. Okay, we'll do one more example. As promised, I want to do an example where we solve for n, because this is sort of the hardest case and it involves logarithms. So we'll do one more of those. So here we have a credit card question, and it's posed in the following way. It says the annual interest rate on a credit card is 24.99%, so really quite high. If a payment of $100 is made each month, how long will it take to pay off an unpaid balance of $2,487.56? So here we have to make some assumptions because it's not quite specified. All credit cards are different, but we'll assume there's 12 billing periods per year, and it doesn't really specify how the interest is calculated or anything like that. But what's happening here is essentially the credit card company or the bank is buying an annuity from you. So the present value formula is applicable here. And what do we have? We've got the present value is 2,487.56. Our payment size is $100. We've got I. So our interest per period is 24.99.2499 over 12, right? We'll assume we've got monthly billing cycles. And, well, we're making these payments each month, so this is reasonable. And N is what we're looking for, right? How long will it take to pay off this balance? So N is our unknown. So I'll write down the formula again. So PV is PMT times minus 1 minus 1 plus I to the minus N over I. We want to solve for N. Right, so let's do that now. Before we plug in anything, let's solve for N. So let's see, first thing I'm going to do, multiply both sides by I. So I times PV is equal to this side. But then I'm also going to divide by PMT, by the payment. And that's 1 minus 1 plus I to the minus N. Now what? Let's add this expression, 1 plus I to the minus N. Let's add that to both sides and subtract this from both sides. So essentially I'm just going to bring this over, so this becomes plus 1 plus I to the minus N. And I'm going to bring this over here, so this becomes minus 1 minus I times PV over PMT. Alright, so we want to solve for N. I wish I had a bit more space, but N is stuck in the exponent right now, so what do? I take the log. I take natural log of both sides. So I've got ln of 1 plus I to the minus N is equal to ln. I really need more space. I'm just going to bring this up here. So ln of 1 plus I to the minus n is equal to ln of 1 minus I times PV over PMT. Awesome. Why did we do this? Well, because we want to get this minus n out of the exponent, and that's what logs do for us. This comes out front, so I've got minus n times ln 1 plus I, brackets here are redundant, is equal to ln of 1 minus I times PV over PMT. So if I want to solve for n, what do I want to do? Let's divide both sides by this thing. So minus n is equal to ln of 1 minus I times PV over PMT divided by ln of 1 plus I. And if I want n, now I just have to multiply both sides by minus 1, right? So multiply both sides by minus 1. Here is the present value formula rearranged to solve for n. not something I would commit to memory, right? I would just commit the present value formula to memory, and then you can rearrange to get here every single time. It's a process, but as long as you understand how logs work, it's not that bad. So now what do I want to do? Now I just want to take all of these things, take all of these, and plug them into this formula. Okay, so I won't write it down, but I'm taking them all and plugging them in. Again, I'm being careful not to round until the end, but what I get is n is approximately equal to 34.41. So of course I can't finish paying this off after 34.41 months, so I'm going to round this up to the next closest month, always round up. So our answer is 35 months. Which is pretty significant, right? After 35 months, you've paid 35 times $100 is $3,500. You've paid $3,500 to pay off this outstanding balance of only $2,487. So anyway, we'll stop here. Thanks.